Hi people, so today we're going to work on 7.4 in our exponential logarithmic booklet, and we're talking about characteristics of logarithmic functions with base 10 and base e. So this is our first intro into logarithmic functions. Now, you and I, we're going to look at them and we're going to look at characteristics and properties, but we're going to focus on the graphs and finding things in the graphs and using graphs to solve problems. That's going to be our focus. So in this area right here, we're going to put some stuff that is good to know about logarithmic functions, but they're not going to be too useful to us. If you also take pre-cal, you'll notice you're going to use this information quite a bit more than you and I will together, and that's totally fine. It's just some kind of base information about logs before we get going. Alrighty, so first things first, a logarithmic function is it's basically the inverse of an exponential function. You'll notice that they have a lot of the same kind of characteristics. They have the same kind of general shape, as you'll see. It has the form y equals a plus b log x, where that a and b value kind of show you how quickly it increases or decreases or whatever, and it'll show you the I'll just show you some characteristics about it. Now, your calculator does not have a log part, so when we do this in your calculator, it's going to look like this: y equals a plus b ln x, or natural logarithm. So they're just like the same forms, just like how we haven't talked about this yet, but sine and cos are basically the same graph, just changed a little bit. Your calculator will only use natural logarithms for whatever stupid reason. Alrighty, so normally we call this a little base. So we call that base 10, where that's kind of it's a subscript where it's kind of smaller and lower, and we normally don't even write that down. So we call that base 10, just like right there, nice. We call that a base 10, but we don't even write that part down. We just call it, that's kind of a common log is what they call it. So we usually just write log x. We don't even bother with that little 10. And then when the base is e, log of base e of x, that's what we call a natural logarithm. And we say ln x. That's how I pronounce it. And then lastly, how to compare logs to exponentials. Well, if I have log with a base b of x equals y, I can kind of move this around to change this to an exponential function. B of y equals x. Now you'll see how this would be a really hard thing to graph in your calculator, b of y, because in your calculator you only have, it's only set up for when y is isolated. So that's kind of why we need to use logs. It's sometimes it's a really good tool. And one place you're going to see logs a lot in, if you continue on, is in science, because it's really handy for things like population or things that grow like crazy or decrease like crazy. So they are really helpful and handy, and if you go into pre-cal, you'll see more of them. You and I are just going to focus on the graphing of them, really. So let's just make up an example here so we can see some of the characteristics of it. So a log function, one version of a log function will look like this, with some arrows on there, where it's got a nice curve, a similar shape to exponential, but kind of in a different direction, right? And in different quadrants than exponential functions. So I'm going to call this an increasing function, because I go from left to right, my y values are getting bigger. So this is an increasing. You won't have to say increasing every time, but it's nice to know that it's increasing. Log. You could write out the whole word, but I'm bad at spelling it, so I try not to. Degree, that's just not something we really say with logs. I just copied and pasted this little area here. How many x-intercepts does it have? 1 right there. How many y-intercepts? None, because it never crosses the y-axis. So 0. Notice that's opposite of what exponential functions are. End behavior. Looking at the left to the right, so left would be down here. We're in quadrant 4, and then we go into quadrant 1. So 4 to 1. Domain. All right, left to right again. Left, our smallest x value looks like it's going to be 0, but it's not going to touch 0, is it? It's going to get really, really close. So we use a round bracket. Then we say comma. Biggest x value. Well, we're going to the right forever, so infinity. Again, round bracket, because we're not actually, it's not really a value we can reach, right? Range, going down, that would be negative infinity to infinity. Round brackets again. Number of turning points, really not something we say with logarithms. So you'll notice that these things are actually very similar, but kind of opposite of exponential functions, right? Let's flip and let's try a decreasing log and just take a look at the shape of that. Alrighty, so a decreasing log might look kind of like this. Similar shape, just kind of, it's like reflected, right? Reflected over the x-axis. So this is, it's a log as well, but I'm specifically calling it a decreasing log just so we can look at the different things of it. We don't really call it a degree. It still has one x-intercept. It still has no y-intercepts. The end behavior this time, looking at the left, we're going to start in 1 and end in 4. So 1 to 4. Domain, okay, 0 still to positive infinity. Neither of those are inclusive. And range, negative infinity to positive infinity. So those stayed the same, didn't they? And return points, yeah, we just don't really talk about that. So that's what a decreasing log could look like, because it's going, the y values are going down as we move to the right. Let's try a little bit more specific examples, and we'll get your calculator in here to practice some of those calculator skills that we know about. Let's try this guy right here, 5 log x. Let's use our calculator to come up with a table of values. Let's graph it, and then I think we'll be able to say a lot of these things. So, beautiful calculator. Clear any of the junk I had in here. Let's graph this. Y equals, oh man, I got lots of stuff in here. 5 log. So we're going to find the log button. It's on the left hand side right there, and you'll notice natural log is right underneath it, so that's handy. 5 log x. I'm just going to adjust my window settings because I definitely had something crazy in here. This is my go-to window setting when I'm not really sure what I'm looking at just yet. Negative 10 to 10. Hit graph. Oh, beautiful graph. Now the thing is, I'd like some values to put in here, right? So if you remember, we've done this before. I'm going to use this little, right here, it says table. Mine's in blue. So I hit second and graph, and it gives me some values. Obviously, I'm not going to include the ones that say error, because that means it's not a point. So I'm going to start right here at 1, 0. That sounds pretty good. And if you don't have quite the same, it doesn't come up the same, maybe it goes up by like 2s or it goes up by 0.5s or something. You see how it says table set at the top here? We go blue, window, and this is where you can kind of change what you want to start at. So start at 0, going up by 1s, something like that. Oops, that's where I want to go. Okay, so 1, 0, 2, 1 point. You know, I'm just going to use 1 decimal place. I really like you to use 2, but you know, we won't be able to graph to that precision anyway. And 4, 3.0. Okay, so that's good enough. We could certainly get a lot more values. This is a good place to go if you just need some values too. Pretty easy for graphing, right? Okay, so I think I'm going to go up by, start at 0 right here. And I'm going to go up by 2 blocks to 1, I think. And I'll do the same on the y-axis. Just so it's nice and spread out, we can kind of see some of the points. Alrighty. So throw in some points on my graph here. Certainly not looking for exact values. I'm just kind of looking for general space that it could go in. And I know what my graph should look like because I just looked at it on my calculator. It should kind of curve here, and notice we never cross that y-axis. We're going to get really, really close to it. We're not going to cross it, and we're also not going to do something like this where we curve back out. I know that's really exaggerated, but I don't want to see it curve away from the y-axis either because that doesn't make sense. Throw some arrows on there too. Good idea. Okay. Number of y-intercepts, there's 1, and where is the, no y-intercepts. I was ready for the x-intercept first, okay. Number of x-intercepts, there's 1 of them, and it's right there. So 1, 0. End behavior, this one is increasing, so it's going from 4 to 1. And domain, you'll notice a lot of these things are exactly the same every time, right? Domain is from 0 to infinity, and range is from -infinity to infinity. Like, those things didn't change. The end behavior, the quadrants changed, but that's about it, hey? Let's flip and try another one. There's a little table down here, but that's meant for the next one here. Yeah, see, it just got cut off. Okay, so I'd like you to try this one. I'm going to pause, do it, and then come back to you. Alrighty, so this is this one. I made a little table of values. I graphed it. Notice I used a different Y scale just so that it would look a little nicer on my graph. And then I filled these out, and actually all these things were exactly the same, weren't they? My x-intercept's the same, and behavior, domain, range, everything was exactly the same. The only thing that would have kind of changed would have been the end behavior if that had been a decreasing function. Now notice, when we had exponential functions, when we had a half in there, like something smaller than 1, we would have had decreasing. But this time it's half, it just kind of increases slower, you know what I mean? Instead of like shooting off, it's increasing slower. So values smaller than 1 don't make it decrease. It actually has to be negative, so smaller than 0 for it to be decreasing. Let's flip. And there's 2 more here. Look at that, a negative guy with a natural logarithm. And the only difference between this question and the last one is when we go to graph it or we use our calculator, we use this natural logarithm button. Like, that's the only thing that changes, and you'll notice the shape will look very similar. All the characteristics will be very similar. It gets pretty repetitive here. So go ahead and try these ones. You'll see the answers in our notes booklet. And that'll be that. Let's take a look at this next one here. Alrighty, so cobalt-60 is an isotope used in medical imaging. It decays naturally over time according to the equation, this business. So there's a typo here. This should be T and this should be P. So just give that a switch for me. I should really change that, shouldn't I? Where T represents the time in years, so that's like our X, and P represents the percentage of the original material that is still radioactive. So over time, less and less is still radioactive, which is great because, you know, radioactive materials are pretty dangerous. State the domain and range of the logarithmic functions in the context of the situation. Now, this is a really good type of exam question because you have to make some kind of educated decisions. Now, if I were to graph this on my calculator, it would look something like this, where it kind of it does cross the x-axis eventually, I believe, but it takes quite a while to do that. So it kind of coasts along the x-axis for a long time. Alrighty, so domain. Domain would be time here, right? And that would mean range would be percentage. So let's think about time. I think time, we're going to probably start at 0, right? And that's kind of how our logarithmic functions usually go. And then our maximum time, This could actually go on for years and years and years, and probably like infinite years, right? Because it will really slowly decay over time. At some point, it's not going to be dangerous anymore, but it will still be decaying. So I'm going to say infinity, because this is what my graph seems to believe as well. Now, this is where I need to be really careful with my brackets. Infinity is always going to have a round bracket, but I need to think really carefully about this one. I know in general we would put a round bracket because it's a log, but in the context of the situation, if I'm a person that deals with this radioactive stuff, there's a set time that I start, right? Like, okay, I dug it, I put it in the hole, that's when I started. So there is a set start time. I can start my timer right now. That's a real value that I'm going to reach. So I'm using a closed bracket or a square bracket there. Now range. Range is my percentage. When I start that timer, I'm going to be 100% still radioactive because I just made this isotope, or I just found this isotope, or whatever, however you do things. So I would say that I start at 100% radioactive, and I would say that's a closed bracket because it should start at the beginning as far as I know in terms of science stuff. I don't really know all that much about it, but there it is. And you notice that's going to be my biggest value because we can't go over 100%, and I always put the bigger value on the right hand side. Now here's my smaller value. Percentage. If I go for infinity years, will I reach 0 radioactiveness? I think probably not. I think I'm going to get really, really close to 0, but I don't think I'm actually going to reach it because infinity years, it'll be 0.1% radioactive, and then infinity plus 1 years is going to be 0.5 or 0.05% radioactive, and then maybe half of that, and then half of that, and yada yada. It's going to continue on forever like that. So round bracket, because I don't think we're actually ever going to reach 0% radioactive. It will just maybe decrease by half every time, something like that. So these are really good questions, this type of question where we have to really think about the context, and then the limitation question. That always comes up a lot as well, right? And so a good limitation for this one would be, like for the domain would be, you can't have negative time, or you can't have negative percentage if they're talking about range. Those are classic limitation questions. I'd like you to try this one here. Actually, let's try this one together. Again, there's a typo here. Alright, so it becomes easier and easier to see the headlights of an oncoming car the closer that it gets. The distance, d in meters, that's going to be our x value, between the car and the observer can be described as a function of intensity, I in lumens, of the headlight brightness. So the closer you get, the brighter it is. So the reason why that's our independent, or our independent, is how far we are kind of dictates how bright this thing is going to be. And the further we are, it's going to be quite a bit less bright. All right, so I'd like to graph this thing. I don't really have any values other than this equation, so I'm going to whip out my calculator and let's graph it, and let's see what it looks like in here. So 350 minus, we use that natural logarithm button on the left hand side, throw in an x. I'm going to have to change my window settings, I know that. I have done this before, so I know what it should go up to. So maybe you can just use the same window settings as I am right now. You know what? When in doubt, you try something and see what it looks like. Woo! That is not what I want. Let's try this again here. Alright, give me a second. Whoops, found my mistake. I forgot the 72 in here, didn't I? Here we go. That makes more sense. I just didn't type it in right. Good idea. Double check what you type in, hey? Alright, now I need to be able to graph this on here, and I need to actually have real values. If this is a test or an exam or an assignment, you have to have real values to graph. I don't want you to just throw a line on there. We threw a line on some of those other questions just for, like, just to look at characteristics, But when you're actually getting, marked for something, I want to see some real values. So I'm not asking you to do like perfect values, or what you pick can totally depend, but we're going to pick some nice values to put on here so I can graph it at least a little bit. So what I like to know is just a couple values along the way here. So I'm going to go second trace, 1 for value. I could totally use my table as well instead. When x is 1, whoops, try again. When x is 1, y is 350. Let's try another one, maybe around here somewhere. So second trace, 1. When x is, let's try 25. Yeah, okay, right there, not bad. Y is 118.24. Now, these values don't matter. I'm just making up values so that I have enough that I can graph it. When x is 50, okay, a little further, great. 68.33. And these decimals don't really matter either because you're not going to be able to see the decimals when I graph it. Let's try one more, 75, and let's call it a quit. Oops, how did I do this? 75. These are just enough values that I can see the points. This is going to be a pretty accurate graph. It doesn't have to be perfect, but it's going to be not bad. What should go along the bottom? What kind of label are we talking about? We're looking for our independent axis, and independent is our distance, which happens to be in meters, I believe, so we need to have it in meters. And I think I'm going to make my graph go up to about 100, and that should be good enough to show the shape of this. So I went up by 25s, and the thing is here is you just need to be consistent. So about this much is 25, going up by 25s every time. It's not perfect, but it's not bad. Now my y values, which is my intensity, so I guess I'll add that on the side here, intensity. And the unit is lumens, so we put that in brackets, lumens. Kind of ran out of space, so I got squished. My biggest value is 350, but when I had that on my graph, it really wasn't that close. So I think I'm going to go even, I think I'm going to go to about 400 perhaps. And, I'm going to go down to about 0, so that should work out. So I'm making kind of educated guesses of what should go along here based on what I had in here. And I was just guessing what should go along here. I'm just kind of guessing and checking as I go. Again, I'm going up by the same amount every time, so 100, 200, 300, 400. It's not the same scale as down here, but it's consistent, right? Now let's throw some dots on here. So around 1 is 350. Not perfect, not measuring or anything like that. I'm just getting close enough, right? Close enough that that's a reasonable place to put it. Certainly not using a ruler because I'm way too lazy for that. But enough that I can show the graph here, right? Sketch, throw a line on there. Now arrows, there's one up here, one down there, and I made myself a nice little graph. So that's for 3 marks on your exam. All right, let's try some of these now. Determine the distance of an oncoming car is 75 lumens. How handy is that? Did not expect that to happen. I do have the answer right there because I already found it, but let's pretend we didn't find it just so we can practice our skills a little bit. So if the intensity is 75, that is a y value. So on my graph, going back to here, since it's a y value, that's a more annoying one to find. We have to go y equals. Don't erase that. We're going to throw in another value right here, y equals 75. Take a look at the graph, and I want to see where those 2 lines intersect. So we go second trace, 5 for intersect. It asks me first curve, I hit enter, second curve, enter, guess, sure, enter. So we end up hitting enter 3 times. Oh my gosh, I'm so silly. Okay, that was x equals 75. This is y equals 75. Okay, good thing I checked because or else I would have just written down that answer. All right, so anyway, x is 45.58. Definitely need a unit. Distance was in meters, so meters. All right, So let's try this next one. What is the maximum intensity of the headlights? Justify your answer. Now, this is a logarithmic function. We did put an arrow up there. This thing is never going to actually have a maximum value, is it? Because it will keep going up and up and up. And if we had looked on our calculator graphs and I put 0.5 meters in there, I would have gotten something bigger than 350. And then if I put 0.1, I would have gone bigger than that. But a logarithmic graph will never actually have a max. So let's just mention that for a second. Log graph will never have a max. I mean, the max would be infinity, I guess. Like, that's not very helpful though, right? A log will never have a max. So in terms of this question, I'm going to say 350 meters. And the reason for that is that in the terms of the context of the question, that's a reasonable value. Like if we're talking about a like a car driving or something like that, being 1 meter away, that's probably about as close as you're going to get to a car, right? So in the terms of the context, 350 is a reasonable starting point. And notice I found that 350 from my equation here. So it's kind of like 350 and then we start decreasing from there. So it's not exactly a perfect maximum intensity because it's not true using the modeling of the logarithmic function. But you're not going to increase intensity forever. You're not going to get closer than 1 meter away from that headlight. So it's kind of a tricky concept there, isn't it? Let's flip. Let's do some matching, and then we'll leave it for today. All right. So here's just some general information at the top here. On the left, that's an exponential function. And on the right is a log. Again, left exponential with an e, and on the right log. Alrighty, so here's some exponentials and some logs all together. Let's see if we can identify them. First one, exponential. Second one, exponential. Log, obviously, log. We still call it a log, even though it's a ln, like a natural log. Natural log, same thing. Which one of these increases? The one that has a b value that's bigger than 1. So this is increasing. That one is decreasing. And if you remember, the 5 or the 2 here, those are the y-intercepts. Okay, here, that's a positive value in front of log, so that is increasing. That's a negative value, that is decreasing. And I think that's enough to tell us everything, isn't it? So, here, we have a exponential function because it's going from quadrant 2 to 1, and it is decreasing because it's going down. So a decreasing exponential, number 2. Again, we have a function going from 2 to 1. This one is increasing though, so I guess we're talking about number 1. Okay, we have a log because it's going from 4 to 1. And it is increasing, so that looks like number 3. And a 1 to 4 function that is decreasing, the only one left anyway, number 4. And that is it for today. I'm going to pause it and then throw up some homework questions for you to give a try, and that's it. Alrighty, here is some homework questions for 7.4. Give those a shot, please, and see how they go. Otherwise, have a great night.